Thank you very much. Can everybody see me? Can everybody hear me? Awesome. This microphone's kind of sketchy, but we'll deal. Our presentation is end-to-end voice encryption. Voice encryption over GSM, a different approach. We have Wesley Tanner, who is a systems engineer for software-defined radio company and has a BS in EE from RPI. There's me. RPI in the house, I see. Me, I'm not really a security engineer, but it says it on the slide anyway. So I am an engineer for a computer company in Cupertino, BS in computer science from UCSB. And we have Keith, who isn't here, sadly, also from RPI. We love you, Keith, wherever you are. Presentation overview. We're going to go over the motivation, the need for cellular crypto, current market offerings, and our approach, a different approach to the GSM voice channel modem. We're going to go over the details, the radio interface, traditional telephone modems over DSM, some of the design choices and issues we're facing. We're going to go into the cryptographic design, and hopefully we'll have some demonstrations that won't fail miserably.
It'll work.
I have faith. Motivation. Where is the end-to-end voice protection over cellular? A lot of people want it, but majority of the products in the market don't provide in the sense that they fail in a lot of different areas. The number one being price. We'll get into that later. We want to make cryptographic cell phones available for the discerning, privacy-conscious consumer.
One sec. It's okay for photographs. So.
Thanks, Wes.
It's a requirement. We have to say it.
That was awesome. Here is a image of the GSM network we stole off Wikipedia. The only thing we wanted to point out is that here's the handset and here is the base station. Those are the only two things you need to realize. GSM cryptography. You're all probably reasonably familiar. We have the A3 algorithm for authentication, the A5 for the actual encryption of the voice channel, or attempts at that, and the A8, which is key generation. Those have both been, well, A5 has been broken horribly, and you have no voice protection on GSM. Even if you did, it's only over the air, and once the data actually reaches the network, you're in clear text, so that should be fun. As the slide says, the moral of the story, GSM cryptography provides limited, if any, security. Your voice channel, to your voice channel. Something else is needed, a cryptographic layer on top of that, or a cryptographic data channel. More on the need of cellular cryptography. Cellular phones have completely supplanted PSTN. I don't think that many people in here have landlines. I sure don't, and I don't really know anyone that does. The cellular companies do not provide meaningful protection for that traffic. And the ease of interception of voice data is kind of ridiculously easy, as we'll show later. Two major classes of intercept: the government-perpetrated intercept, the TLAs, authorized and unauthorized. That's pretty much what I want to say on that. Non-government perpetrated, the more interesting ones, by private investigators, business partners, economic espionage and such. The product on the right is a device you can buy for a couple of $1,000s.
These devices are relatively expensive, but in the coming years, it's expected that with a cheap A to D converter and some special software, you can do this for a lot less money. So it's going to become more of a reality for private intercepts.
Thank you, Mr. Tanner. Government intercepts are probably the most common, undetectable, sadly untraceable, done at the higher levels of government. Data for the reported intercepts. In 2000, there were 1,700 intercepts. That covers everything. And 1,500 of those were portable devices, cellular, telephones, satellite phones, etc. That's quite a large number. Here is a chart of the increase in cellular wiretaps. Actually, yes, cellular wiretaps, portable devices. As you notice, intercepts have doubled since 2000. The trend appears to show that it's increasing. You could probably all notice that from the last slide. What's interesting, though, is there's no massive jump after September 11th. We won't go all tinfoil hat on you, but which kind of implies they are obviously doing more wiretaps, so those aren't getting released in those numbers. There's also a GSM spec for lawful interception. It's kind of interesting. They make it rather easy. It's actually built into the GSM specifications to get output product network data, which is your, location, type of call, parties, numbers, of course, the product, which is the speech user data, SMS, everything you take for granted to be reasonably private. It's not. Here is a diagram of a lawful interception. Note the shady-looking law enforcement agent, the intercept request, and the data coming back to the LEA. Very interesting. The moral of the story, too, is even if the GSM crypto was sufficient, as I said earlier, the protection from the handset to the tower is capable of being... Even if the over-the-air voice crypto is secure, you still have the over-the-wire cryptography. Over-the-wire clear text, which is easily interceptable, as noted from the last diagram. So,
there's a variety of products out there already that address this problem, and we got a chance to see the Cryptophone guys present their products at Hope last year. Apologies, is it better? The Cryptophone guys presented their product. It's slick. I've never used it, but it does address this problem. There's the Sectera device by General Dynamics, and that's really used more... that's basically available to a military and government contract. There's the Encore Crypto smartphone. There's not a whole lot of information about this product out there. It's kind of I was unable to find anything about it. And there's several other Vapor products that their web presence has gone up and down, and they're no longer available, so can't say anything about those. There's There's a new government standard that's looking to replace the STU3, which is what they use typically to provide Type 1 voice crypto. It's the Future Narrowband Digital Terminal Standard. This has a minimum requirement of 2400 hertz for voice. It uses very standard things like MELP for voice encryption, or for voice compression, and AES for voice encryption. And there's more data about this on Wikipedia. The problem with the current products, they all probably work very well. I've never used them, or I've never seen them demonstrated. But they use the circuit switched data channel. I was never offered this as part of my consumer package, and I think I've heard that you need to pay roaming charges for in some areas on this. So it's not as ubiquitous as the voice channel itself. There's longer call setup times associated with it because it's a modem. It has to negotiate the connection, and there's a higher latency, but it's better than the packet switch services that we use for like GPRS for typical internet over a cell phone.
Also, if you can get circuit switch data, it's usually rather expensive, which is kind of irritating.
And it's meant to carry data, not voice, and data is not forgiving with bit error, and voice is. You can have large numbers of bit errors in your voice stream, and have reasonable voice quality. So you don't need it to retransmit, and for data you do. And I mean, the biggest problem is that these products are not available to you or me. They're very expensive, or they're for military or government use only. And a solution should be available to you and me. 3G will probably take care of a lot of these problems. because it is high bandwidth data, and the data suggests that it will be low latency as well. It hasn't been rolled out everywhere. It actually is in San Diego, and I believe San Francisco. I don't have it, but it may solve the problems, but again, it's not available to everybody today. And we're proposing a solution, which is what we've been researching for the last couple months, is developing this, developing a modem that will work over the 2G voice channel and the 3G voice channel. And it involves a bunch of technical disciplines, which makes it an interesting problem. And that's all I want to say about that. Basically, the voice channel on GSM is a subset of a generic voice channel. Basically, the tricky part about the GSM channel is that it's highly compressed. And if we get this product, a product to work on the GSM channel, we can use it on anything. You can use it over two-way radio, voice over IP, or normal packet switch telephone networks. And the goal is to have an integrated thing that works over all these protocols, and all these systems. So that's the goal. And this is the proposed system block diagram that I don't know if it's easy to read. But basically, you have your input voice stream that goes into some kind of modem and goes through the GSM channel, through all the networks, and comes out the other side undistorted. The project goals are basically to maximize the voice quality and provide strong crypto for privacy, and to minimize the distortion. So you want to have good sounding quality audio and have it very secure. I'm going to blow through some of these quick because it's highly involved and takes too much time. But basically, the GSM voice channel is a low latency, highly available channel. It has a friendly billing system. You can use your minutes instead of more expensive data packages. However, the voice channel uses strong compression, which causes distortion for certain types of signals that you pass through it. And therefore, you need to pass through things that look like speech so they're not distorted. This is a pretty busy slide, but it's basically calculating the data rate over the GSM air interface. And this is a breakdown of the GSM voice frame by speech parameter. It works out to 13 kilobits per second, and there's 260 bits per frame, and those are sent every 20 milliseconds. And all these parameters here are what we're trying to exploit to enable us to create a waveform that will work over in this frame without significant distortion when it goes through the channel. And this just shows that there's a 8-to-1 compression. Your input on a typical GSM handset is 8 kilohertz sample rate audio at 13 significant bits. And that works out to an 8-to-1 compression when you go down to 13 kilobits per second. The official name of the 2G GSM voice channel is the top bit. It's a long way of saying that it uses a complicated compression to achieve its goal. And the input is PCM on a uniform quantized data. This is another busy slide. It basically shows and this is from the 3GPP website. A lot of this data is available there. It's the voice encoder. Your speech samples go in on the left, and your voice, the parameters that describe that speech, come out on the right. And there's a bunch of complicated processing in the middle, and it's highly nonlinear. And this is the speech decoder, the synthesizer. It takes those inputs, parameters, and spits out synthesized speech that's a very clear representation of what you originally put through the channel. I'm going to blow through this one. Basically, the processing involves short-term algorithms that determine what the short-term content is. There's a long-term prediction that gives you your lag and gain, and the coder also determines the pitch of your voice. And all this is fed through this coder. You get a residual air signal out, and that's also encoded. So all these parameters do a good job of representing speech. When the voice packets go over your GSM radio, some bits are protected from transmission errors and some are not. The Class A bits are. I think it's about 36 bits that are actually protected. Those are the most important bits. If you flip one of those, it's impossible to have intelligible speech. If the other bits are flipped, it's possible that you can actually understand the audio coming out of the phone. There's an RFC about this that goes into more detail. And this is a slide we threw in just showing a typical speech pattern. It has a pretty distinct shape. I'm sure a lot of you have seen that before. This is 8 kilohertz sampling rate, and it's about 6 seconds of audio. And this is a zoomed in version. It shows that there's a certain pitch over the frame. And I always wondered why you couldn't use your traditional telephone modems over the GSM channel. So I'm going to talk about why some of this might not work. Your typical telephone modulation schemes are listed here in order of bit rate. There's the 300 all the way to the 56 kilobit per second that we're pretty used to these days. And they're listed by modulation type as well. So they use different schemes to encode the audio. And I'll give a quick description of 56 kilobit per second modem. It uses basically shaped voltages, or pulses over your analog pair. And these represent bits that you're sending. And those are converted to digital signal when it gets to the telco office. These voltages are held on the line for 125 microseconds, which is a pretty short amount of time. And there's 8 bits per pulse. So there's 256 discrete voltages that go over your line. And in North America, we use only 7, so we have 56 instead of 64 kilobits per second. But in reality, the analog lines are not able to discriminate. It's hard to discriminate between the 256 levels, so they typically use less. And that's why it negotiates a slower connection. And this is a high-level diagram of talking from one analog voice modem, V.90 modem, to another. And basically you can see the pulse. You go through analog, comes out digital, goes back analog. And one of the 1200 bit per second modems, they use a phase modulation scheme. I just threw this one in. It's a Simulink model of a PSK modulator. And it turns out that voice codecs are not, it's not important to preserve phase information for voice traffic. You can perceive, it's hard to perceive changes in phase and timing on voice. And so that information is not preserved over the channel. And this is what PSK kind of looks like. On the right is the time domain signal. And you can see that it's a sinusoidal shape. And there's discontinuities where we're adjusting the phase. One phase represents a 0, one phase represents a 1. And the spectral content, and you can see the bandwidth it takes up. So I'm blowing through these fast because I don't think we got the time. But I want to run a demo right quick of using frequency modulation over GSM. And what frequency modulation really is, you're encoding one tone as a 0 and another tone as a 1. And those tones are flipped back and forth and at a certain rate so that you send your data that way. Now we're going to show how the GSM channel distorts that signal, making it impossible to decode correctly. That would have been bad. All right, this is a quick aside. We did our modeling and work in Simulink and MATLAB. It's a numeric processing tool that is pretty quick to prototype on. It allows you to rapidly throw something together and throw information at the channel and see how it behaves. The actual voice channel we're using, our model, came from the 3GPP website. They have all the reference code available. And so it's in C. You can compile it it compiles basically in any architecture. And so we threw that code in with some glue into Simulink so we could model this. All right, so this is running at 100 bits per second. Hold on right quick. This is the output spectral content going through the voice channel, but let me switch it over to just straight pass-through. You can see the tones. Oh. You can see the tones going back and forth between the 0 and the 1. The lower, closer to the 0 is a 0, and further out in frequency is a 1. You can see them flipping back and forth. And you can basically determine at any given time which one's which. It's easy to discern when it's a 0 and when it's a 1. If you put this through the voice channel itself, you can see that the pulses they look a little more distorted. It's harder to tell at any given time what the actual tone is going through there. There are these blips and blops, and it's harder to pick them out. So that's just a visual representation of what kind of distortion you would expect to see on this channel. So I'll go into some technical details about what we're proposing to do, which is to make a modem, a modulation scheme that will allow you to pass data undistorted, cryptographically secured voice data through this channel without having it flip bits. There was a group in England that we discovered that is doing the very same thing. They've managed to get a 1200 bit per second link over GSM using a similar scheme. Basically what they do, they take their input encrypted voice, which is encoded at 1200 bits per second, which kind of sounds like a speak and spell. It goes through basically a codebook lookup system where it has a list of waveforms that will actually pass through the channel correctly, and it will synthesize speech based on some of those parameters. It's a relatively simple approach. They're exploiting the fact that speech has very specific qualities and parameters that you can readily, the channel is able to distinguish between those different things. Now our system is very similar. We're going to try to take what they've done a certain thing. They've taken these parameters, they've synthesized things. We want to figure out a better way to characterize the voice channel itself and see if we can come up with a higher bit rate. We've decided that 2400 bit per second audio is much better than 1200 bit per second audio, so much so that it's worth investigating how to make that happen. And again, there's our proposed system block diagram. And this is a high-level diagram about the flow of data through the system. So you have a microphone at one end that's going into an analog to digital converter. So you get your audio samples. You put that through a speech compression routine, and the output of that is the 2.4 kilobits per second. And you run that through some kind of crypto. We're proposing AES, block cipher, and run that through a error corrected coding.
More details on that later.
Huh?
I said more details on that later.
Right. And error corrective coding, which basically means that you can encode the data in such a way that if there are errors on the channel based on either through the distortion of the GSM voice channel or drop frames over the air, as if you go through a tunnel or inside a building, it'll be able to correct those errors or at least detect them. And finally, going through the modem that we're proposing to develop that'll generate valid speech waveforms that'll work over the channel. And those are fed through directly into the speech codec on the GSM phone. And they go through to the decoder on the other side, which is basically the thing in reverse. This is showing. Let's do the demo first. I'm going to demonstrate some of basically using a simple approach to the problem, trying to determine how the GSM voice channel will corrupt the data that you pass through it. So what we're proposing is taking, using the voice channel against itself, using the speech decoder as the modulator, and the speech encoder as the demodulator. So we're going to fill the speech frame up with random bits and see how that will perform over the channel and see what distortions happen. All right. This is another Simulink model that we've thrown together that shows in the middle of this block right here is the speech channel itself, and we're proposing to use the voice codec of GSM against itself. The decoder is put on one side, and we're going to fill the frames up with random data and see what happens on the other side. This is what it looks like on the output. Again, this is random. We're filling the frames up randomly, and it's generating what looks like valid speech information. It looks a lot like what we saw earlier as far as what the time domain signal looks like. This scope shows the bit error rate through the channel. I'll run this one more time so you can see it settle in. It's taking the average bit error. Along the x-axis is the bit position inside of the frame, and into the page is the frame number, and the amplitude is the number of bits that were flipped on average. Let's run this again. Oh, it's very angry at me. I don't even know what that means. Anyway, point being, the bit error rate settles to about 25%. So 1 bit out of 4 is flipped when you put it through, like just using a rudimentary system like this. And we propose that our research will continue as far as developing a scheme that is able to pass a high bandwidth amount of data through that's acceptable speech quality that will minimize that. 25% is far too high to pass meaningful data through. MATLAB for Mac is not very good either, by the way. Side note on that, there's a free MATLAB. I don't know if you guys know about Octave. It's basically MATLAB minus the $100,000 fee. It's available online. You can search Google for it, Octave.
Thank you, Mr. Tanner. I want to take a slight segue for a second and go back to what he was saying about 3G solving this issue. I think it'll solve some of the issues, but if you can purchase a data channel that is high bandwidth and low latency to do voice over IP off a regular cell phone, that kind of cuts into the market that cell phone providers have today. And I'm kind of worried that they might take steps to prevent that, but we'll see when they actually start properly rolling things out. Here we have our network stack, or stack. On the top, the voice channel, which is a low bitrate voice encoder, 2.4 kilobits per second. The secure channel, which we'll go into in just a moment. The modulated data channel, which is the voice modem and the ECC. And on top of, those are all on top of the GSM voice channel and, of course, the GSM network. Otherwise, the bits wouldn't go anywhere. Channel expectations. We had to make some decisions and do some research on what we could expect the lower levels to behave like. Detected and fixed bit corruption will be common. Undetected bit corruption will be rare, but we'll deal with that. Detected frame loss depends on network quality and is reasonably common. You most likely hear dropped frames during your cell phone conversations all the time. We hope to have no undetected frame loss. as I said, frame loss and undetected bit corruption will produce garbled speech, which is pretty much similar to what you hear nowadays. So it's what cell phone users are used to and is a acceptable error state. So our threat model, who are we trying to protect against? Of course, industrial espionage, foreign governments, anyone with $10,000 worth of equipment, and of course TLAs, those damn TLAs. Three-letter agencies, not acronyms. What are we trying to protect against? Break of our voice privacy, loss of confidentiality, break of authentication, the loss of integrity. The current threats in our threat model are dropped frames, frame replay, frame bit corruption, partial frames, and of course cryptographic attacks. So dropped frames, as I said earlier, we should be able to deal with as we can detect and increment our counters for that. Frame replay will either break the GSM, will either upset the GSM stack and break the call, or will corrupt the cryptographic channel, which will end up with a error state, like the one we were talking about moments ago. Bit corruption will just add slight blurbs or garbled speech, which shouldn't exactly deviate much from the error state as well. Partial frames will be interesting. Probably end up corrupting the call as well, or hopefully getting the GSM call dropped. We're currently looking into that. Cryptographic attacks, those are the fun ones, of course. We're hopefully picking strong enough crypto and strong enough protocols so that these can be avoided. Of course, these are all closed source protocols. Yeah, I'm just kidding. Channel availability. Increasing the availability of GSM calls is really kind of outside the scope of this project. It is ridiculously trivial to block GSM voice channels, as you would probably notice from being inside casinos and getting no service. You can purchase cell phone jammers, a lot of places have, for not too much money. You can corrupt frames over the wire. You'd have to be a TLA to do that probably. And you can also just request from the service operator disables the voice channel or disables the account altogether. So as you can see, it's not really practical for us to attempt to increase availability of the voice channel. We're hoping, and it seems that channel will not significantly decrease. The availability of the calls will not significantly decrease using our scheme, which is good. Secure channel. Secure channel provides voice privacy. It does not provide message authentication. The reason being is we're working with a reasonably low bandwidth, and we don't have space for Macs or anything like that, sadly. So we're relying on the authentication in the key exchange, and any manipulation of the data going over the air will cause garbled speech, but will not break the cryptographic channel. Here is a wonderful diagram of the initiation of the secure channel. Div Hellman, variable key sized, being hashed into our session key, into a send and receive key, and our two counters, which you'll see more of later. Here's a general diagram of our encryption model. This is for send, of course. Session key is generating a send key through SHA, which is then used with AES in a counter mode with our send counter. And I said before, when a frame is dropped, we will have to increment the counter to stop from destroying the entire secure channel. Once the key stream is be generated, that is XORed with the voice data, which creates our ciphertext, and which is passed off to the voice modem, the modulated data channel. There's many more details in the white paper, which is available on the web page. Key exchange. We're utilizing Ferguson-Schneier key negotiation protocol because it is a wonderfully strong design. I like what Schneier and Ferguson have done. And the key size is flexible, which is extremely key in this situation. We have two ends of this. We can have extremely limited hardware, having a Bluetooth headset that's doing the voice encryption for you, extremely lightweight, and we need to save as much, use minimal CPU processing as possible. And we have the other end where you're running this on your laptop over your generic landline. Not that any of you have a generic landline. So we want to have the flexibility that entails. The second choice was station-to-station protocol. I definitely like the fact that you can encrypt the signatures in station-to-station, but it lacks the key size flexibility, which really kind of killed it for me. Thanks for deleting that slide, Wes.
No problem.
Oh boy. Here's the key exchange. As described earlier. Alice generating, I'm not even going to go into that. You can read details of that in the white paper. I do want to make a comment on authentication. Most of the products, and the one even detailed by Zimmerman, rely on you reading a section of text back over the phone line to the other person to make sure the Diffie-Hellman key did not break. There wasn't a man-in-the-middle attack on the Diffie-Hellman key exchange. I don't like that. Not on a channel where you only have 2.4 kilobits of voice data going over. The possibility of someone being able to spoof what your friend's voice sounds like on a channel that's that low bitrate is quite possible, and that kind of scares me. So we're attempting to use DSA for authentication rather than relying on the person reading the keys back. Reading the hash of the keys back over, which really kind of scares me. Also, I think Cryptophone, G10, and the other products do that. They have better voice. They have a higher bitrate voice encoding, which should make that not as easy an attack, but it's still definitely possible, and that really kind of disturbs me. Conclusions and questions. Also, if you have any questions via email, we are available at info@cellularcrypto.com, where the slides and all the other MATLAB code and Simulink code are for your viewing pleasure. Also, the white paper will be up there momentarily when I can actually get onto the network.
Oh yeah, to reiterate, the point of this is to create a generic system, a scheme. It'll work over any type of voice link. It happens to be that GSM is pretty difficult due to the large amount of compression. And so if it works over GSM, it'll work over anything else. That's the idea. And that's what we're trying to do.
Awesome possum.
And also, we only had about 50 minutes to do this, and we had a lot of technical information that we had to gloss over. But hopefully the point got across. And it was hard for us to frame this in a way that people could understand, just based upon the fact that a lot of it has to do with voice channel stuff. And
right, it covers two areas, very complex GSM voice channel analysis and a voice modem, and then it covers the cryptography. We attempted not to go into too much detail, but you can read the majority of that on the white papers.
We got a question, but we probably need a mic.
Did you look at DEC or GAP?
I'm not familiar with DEC gap.
You, sir.
Let me make sure I understood the salient parts. The voice modem that you're proposing will have 2.4 kilobits, and the simulation that you're running at the moment keeps your 25% error rate?
We just try to just for the demonstration purposes, a test modem, basically just using the maximum amount of bits in that channel. If we're sending data at the 13 kilobits per second, if you send data at 13 kilobits per second, you get 25% bit error. And so we need to generate a modem that is much more resilient to the distortion involved. So that probably implies using a lot less of the bandwidth available. Yeah, go. Go ahead.
Clarification purposes, so did you build that modem that can transmit at 2.4 kilobits?
No, it's a work in progress. Yeah, we have not actually developed a 2.4 kilobit per second modem as of yet. It's an ongoing process. We basically built the models to work on that kind of design. We're at that point at the moment. Yeah.
Yes, we hope to have something that's usable in.
Hopefully, my graduate program will allow me to discover this stuff further and give me some amount of funding.
Good plan. Any more questions from the audience? You, sir, in the back.
I believe the question is how many bits, like in our random test, how many bits were preserved? We have a 25. If you use the entirety of the bits of the GSM frame and you twiddle those randomly, you get one bit flipped out of every 4. And those errors are basically distributed evenly across the frame. There are some bits that are more persistent. They will stay. They will not be as flipped as readily, but for the most part, the errors are evenly distributed. I don't know if that answers your question, but.
Excellent. Any more questions? Closed. If anyone wants to talk to us, we'll be in the bar for the rest of the week. And thank you. You've been a wonderful audience. We love you. Especially you right there, Lumpy Lump. And Simon Cooper. Fed. Total fed.
Let's go, mate.